Welcome to my video about quarks. Before I say anything, my research question, how can we get evidence that quarks do exist? And my claim, quarks do exist through the Stanford research in 1960s through 70s, and atoms relying on quarks to create other phenomena. So with that being said, what is a quark? Quarks are these really small particles that make up an atom, and they can either create hadrons, protons, neutrons, and other particle variations. In your middle school or other science classes, they said the smallest thing in the universe was the atom. That was completely wrong. Don't trust the teachers who say the atom is the smallest thing in the universe. They like to spread misinformation like that. The quark, the smallest thing in the universe, 10 to the power of negative 18 meters, which is incredibly small to the so-called smallest thing in the universe, the atom, 10 to the power of negative 10 meters. In Keith Cooper's article, Quarks, What Are They?, he describes quarks that they are so small that they almost have no size at all, and are little more than points. But there's also another particle within quantum physics that's 10 to the power of negative 35 meters called the Planck length. But I'm not gonna go into that because I have absolutely no clue what the hell that actually is. Yeah. Anything that is not a particle makeup of quarks themselves, and electrons, they have superposition too. They have this property called superposition, meaning you can be in two different places at the same time. Another weird thing with quarks during superposition is that they can be in every single state of matter at the same time. But you can't just look at this actively happening because quarks are very secretive and put on a character for the world when they're being looked at. Once observed in the state of matter and position they are in will not move or change. That is another way you can think about how superposition works, is when the quark is in an observed state, it will also be moving around rapidly as if it weren't. To explain how superposition works, let's just say these two are the same quark. While we are observing, it won't move. So this will be our observed, and this will be our non-observed. While the quark is being observed, it is still moving around rapidly, but we cannot see it happening because we are observing it. But still in the quantum world, it is still moving, therefore it's in the same two different places at the same time. So how are quarks found? Quarks are very small, so how does one even find a quark? To be fair, all of it was completely found by accident. The original tests were injecting an electron into hydrogen, and what they found was that an electron bounced off the core of a proton, and they were like,
hold up, wait a minute, something ain't right.
In the SLAC article between 1960s and 1970s, they were testing how to find quarks in different flavors and strangeness and tops and bottoms. Not joking, but these are actual things to find properties of a quark by literal strangeness. In the next year of finding evidence of a quark, they upped the radiation of their instruments to see if it would change. It didn't. But what they decided to change, though, was their momentum transfer, which actually showed better results of elastic and inelastic collisions. GeV, or EV, meaning electric volt, and EV, the representation of energy gained or lost by a single electron or proton when it moves across electric potential difference of 1 volt, which is a whole lot of energy. G, or giga, means it is in the billions. Also, if you were questioning how do you even have a number for momentum transfer, it is Q2, or also could be written out as Q2. It doesn't matter, surprisingly, and the number will always be negative. Scientists in Brookhaven National Laboratory use a huge RHIC, or relativistic heavy ion collider, to throw ions into each other, colliding them. In 2010, they collected enough evidence to show the public their discovery of quark-gluon plasma, What they had done was get 2 gold ions and collide them into each other. What had happened was, for a split second, the temperature had reached 4 trillion degrees Celsius. I tried to calculate how much that was in Fahrenheit, but every calculator I used said hell nah, and I was a little bit too lazy. But then I actually searched it up, and it wasn't that hard. Times 2 plus 30. So if I'm right, that is 8 trillion and 30 degrees Fahrenheit. Or just 250,000 times hotter than the core of the sun. In barely a second, actually quite a bit of not long of a long time, Brookhaven National Laboratory said the state of matter existed for less than a billionth of a trillionth of a second, while also saying scientists knew they didn't know they made a new state of matter at the time. They also concluded that quark gluon plasma was the same thing that was made after the Big Bang, not that it had caused it. How does this even involve quarks, you ask? Well, the temperature being so unfathomably hot that protons and neutrons were melting away, which separated all protons and neutrons in the atom and took apart the quarks inside as well. Another article that had referenced the SLAC article about the finding of the last quark being the top quark. The top quark wasn't found until 1995, but the bottom quark was found in 1997. The reason why the top quark wasn't found until then is that that thing was so heavy and unstable that they had to get replacements to their equipment to even try to find it. They decided to look for its decay into W boson, or B quark, aka the bottom quark. The big problem with that was that the bottom quark was so energetic and W was so unstable that it would quickly decay into particle jets. They could kind of get the top signature, but with its decaying showing a less interesting background collisions, that this was the article that described it as, that they wanted a real signature that they can replicate. With much trouble, they were sure that the energy output to even find the top quark was 77 GeV to above their instrument's energy output they could even use, which was 315 GeV. Luckily, in 1992, they got the top quark to reveal itself when hitting 91 GeV. Throughout the rest of the decade, they used their equipment to isolate the top quark even more. They managed to move through protons and anti-quark energy fields of 1,800 GeV. They found the mass of the top quark was about 176 GeV, which was almost the mass of a gold nucleus, which was 197. Pretty much the stuff after that in the article was stuff that wasn't kind of related, but still kind of is. I was just lazy to go read the rest of it and put it in here. But the amount I had put, it gives off a good amount of information without having to read the entire thing.